So yeah, we are Franz, Martinache, and Elodie Choquet. We are the co-head of ASHRA, which is a Science Council for High Angular Resolution instrumentation, and we are here on behalf of Karine Perrault, who is INSU delegate for ISO instrumentation. And unfortunately, she couldn't be there because there is a ISO Science Council as we speak. So she asked us to present her slide on her behalf. And so we are here to talk about, to give you an overview and a status update of the ELT and its instruments. And so Karine highlighted that she has prepared this presentation with contributions from the ESO ELT Program Science Office, in particular from Michele Cirasuelo, who is in charge of instrumentation for Andes and Mosaic. So what's the ELT project? I guess you have heard of it already, but it's the next ESO observatory. It's going to be an optical telescope with a diameter of 39 meters. So as you can guess, with this kind of project, everything is out of scale. You can see here the dimensions of the whole structure. It's a 65-meter high telescope, so I calculated that it's like 20 floors structure high, and a width of 71 meter, including the two NASMIT platforms, on which you can actually fit a single 8-meter telescope on each of these platforms by themselves. So yeah, everything is really out of scale in that project. So it's going to be installed in Chile, in Cerro Armazones, and the first flight is planned for 2028. It's estimated to have a lifespan of 30 years. And with a budget for everything of 1.45 billion euros. It has 4 first flight instruments that have been selected as a first phase, Mikado, Morpheo, Harmony, and Metis, and 2 first generation instruments that were selected afterward on a second phase, Mosaic and Andes, about which Franz will give you more details. Maybe the important thing here is that Franz is actually co-leading the deputy PI of the Harmony instrument, and Mosaic is Franz is PI of the Mosaic instrument. So we have important contributions to to ELT instruments. About the location, so as I said, it will be located in Chile in the Atacama Desert. It will be only 23 kilometers away from the Paranal observatory, so you can actually see the Armazones and the ELT from VLT, from the VLT observatory. In terms of altitude, it's slightly higher. It has an altitude of 3,000 meter altitude compared to 2,700 for VLT. So again, it was selected as an excellent site for optical observations. So the construction is underway. Actually, just a year ago, there was only the concrete that have been built on the site. Now, 1 year after, the whole dome is under construction. Everything is going super fast. In fact, if you can check on a daily basis the webcams of the site, where you see how things evolve day after day. So as I said before, everything is out of scale in this project. You can see here a few numbers, like the weight of the dome is 6,100 tons. The weight of the main structure is 3,100 tons. And there has been like 33 million bolts used to construct the structure of the dome. So yeah, everything is a technical challenge in this project. You can see here the azimuthal structure of the dome seen from inside. And one of the first milestones was also reached earlier that year in January with the first rotation of the dome that you, yes, thank you, Franz. that you can see here. So it was not the motorized rotation. It was like a manual rotation made with hydraulic strands, but still it's an important milestone for the project. It's moving ahead, and we are going to have this telescope built pretty soon. About the optical design, it's a 5-mirror optical design. The primary mirror, as you know, is a 39-meter diameter telescope that is segmented. It's built out of almost 800 hexagonal mirrors, 1.5 meter long. The collecting surface is about 20 times more than the 8-meter UT telescopes at VLT, so 20 times more sensitive. And so to make this primary mirror work as a 39-meter telescope, there will be 4,600 edge sensors that make sure that the full surface, all the segments are co-phased together and aligned with respect to each other with a precision of tens of nanometers, which is critical to have exquisite image quality for your observations. In terms of status updates, the mirrors are being manufactured, and the first segments have actually arrived earlier this year in Chile, where there will be coated in situ in Chile. So that's for the optical design. Apart from that, and for the structure of the dome, apart from that, there are actually a lot of activities going on many topics, both in Europe and in Chile, not only for the optics, but also for mechanics, electronics, control systems, and for the full infrastructure of the observatory. Both, in fact, at Armazones, at the ELT site, but also at the Paranal site. Here you can see, for instance, the photovoltaic power plant, 9 megawatt photovoltaic power plant of the ELT observatory. So it will be fully alimented with solar energy. So that's work that is developed by ESO, but it's not only work that is done by ESO. The whole community is also engaged in the development of the observatory. And in particular, there has been a number of working groups that have been assembled and created by ESO, engaging the community to prepare for upcoming ELT observations. There are 13 working groups involving more than 170 participants. So if you want to take part to these working groups, there are really a number of on different topics. If you are interested in any of these topics, you are welcome to join any of these groups. It's really a collective effort, and ESO is really willing to engage the community on that. Now I'll pass the mic to Franz about the instruments.
Thanks. So the first take-home message is that this giant thing that we've all heard about for like the last 20 years is actually coming online, and it's being built, and it's moving, and it's real. So that's a very important thing. The bulk of that work is really carried out by the ESO teams and the industrial contractors, but there's another aspect of the activity that is taking place within labs across Europe and across the world, and that is the construction of the actual instruments that are going to feed, to benefit from this giant telescope. We've already mentioned the fact that there are 4 instruments as part of this phase 1, and 2 instruments which are currently undergoing their phase B. So if you are unfamiliar with large project parlance or ESO parlance, the stages we're talking about are that of final design review, which is the point at which you start actually building the instruments. And in this case here, the preliminary design review, which is a phase at which you start typically prototyping parts for the different subsystems that are critical to the success of the different missions. And so those instruments are Metis, Harmony, Mikado and the add-on Morpheo. And then we get, those are the phase 1 instruments, and then we get Mosaic and Andes. And I'm going to go through the different projects to show at what is the level of maturity of the different things. Although the word review suggests a very an event that is happening over a finite amount of time, it turns out that those reviews are multi-year processes that are split into sub-reviews. And there's an incredible amount of work that's being carried out by the teams within the institutes that are building those things to make those instruments come about. This is like a complicated representation of all of the capacities of the different instruments in terms of field of view, spectral resolution, and wavelength coverage, along with a timeline and comparative timeline that just shows the level of maturity of the different projects. We see that, for example, Métis was the first to actually reach FDR and the FDR for Harmony and Mikado Morpheo are ongoing at phase at the moment. And then we get Andes and Mosaic, and we even get a 7th one, which is the planetary camera and spectrograph, the sort of equivalent of Sphere that is just about to start its phase 0. So it's another important aspect for our communities. You can see that the telescope is covering a broad range of spectral resolutions as well as spectral coverage. So we go from about the shortest 0.5 micron or 500 nanometers all the way to the 13 microns bandpass. And because it's so complicated to read, we're going to look at things displayed graphically so that you can map out the different instruments and where they stand in this parameter space. So you get spectral coverage in this direction and resolving power for the instruments that do feature some significant resolving power, as well as the coverage for the imaging instruments. So you see that all instruments are occupying specific niches that are complementary to one another in terms of especially wavelength coverage. And you have a powerful combination of IFUs and multi-object spectrographs and slits and whatnot to ensure that we get a very good and powerful tool to explore all of the great science cases that you are going to come together about. The first instrument, and so each of these is going to give you an overview of the different instruments with the maturity level. And so here we start with the Mikado, for instance, that whose last FDR review, the last of 4, is actually going to take very soon this summer. You get the composition of the international consortium, along with a highlight of the French laboratories and the people that contribute to these instruments with their responsibilities. References to papers that describe the science cases. And you're going to find boring things like exoplanet and solar system, but you're also going to find exciting things like galaxy formation, evolution, and AGNs and that sort of stuff. Here you have an example of how real things are, because you get the what is called the single conjugated adaptive optics system part of Mikado that is working and is going to be one of the major contribution of the French instrumentation team. One common trait that you're going to see about a lot of these projects is that a lot of the French contributions have to do with bringing high angular resolution capability to this telescope, because although you're going to gain a lot of sensitivity simply from increasing your aperture size, if you bring the resolution to this diffraction limited, you are not only gaining as d squared in terms of sensitivity, but d to the power of 4. And this is where the true power of these telescopes really start showing. Other instrument is Métis, which I mentioned has already passed its FDR. In France, the contribution is essentially born at CEA. And here we have some specific contributions which included the manufacturing, the creation and the design and manufacturing of cryomechanisms, because it's an instrument that operates in the far infrared. We need the cryo mechanisms. The characterization of coronographic masks and the characterization of infrared detectors. And again, you get references to papers and the names of the COAs and the French scientists that contribute to this instrument. Then we get Harmony, whose FDR you see is ongoing and is going to process till very likely 2026. We're really talking about multi-year processes for these reviews. A specificity for Harmony is the fact that we have a pretty big French involvement in the PI team and the project management team. And again, you get the French labs. For Harmony, you see that there's prototyping activities going on and contributions to a lot of things going from the design and the integral field unit, again, single conjugated adaptive optics and laser tomography adaptive optics. All of the ancillary things that you need for laser guide stars and another thing that is common with Mikado is also the development of a high contrast module to try and prune the low hanging fruits because most people don't really want to wait for PCS to get to that point. Then we get Morpheo, which is an add-on that comes to Mikado. Morpheo increases the adaptive optics capability of Mikado, which by itself is only operating as a single conjugated adaptive optics system. Here it's going to extend the field of view capabilities of the AO correction, and that the French contribution involves the manufacturing of quite a few laser guide star wavefront sensors, of which you have a structure analysis representation right here. Again, we get Choquet ship in France and references to the papers that describe the science case for this specific module of Mikado. And finally, we get two phase two, the two phase two instruments, Andes, that whose contract, in fact, we should have written 2024. It's not 2023. The contract was just signed a few days ago. It was announced. And here you get, again, the names of the people in France that are involved in the instruments, papers to the science cases. And over here, very important for this specific community, I assume, Mosaic, with, again, heavy French contributions and PI ship, actually, with references to science cases and web pages describing the instrument in greater details. Now, the ELT happens to be the one of three extremely large telescope projects that include the GMT and the TMT. And so you get some here like a representation of what GMT is going to look like. We can see that in terms of timing, we're very close to the timing realization of the ELT. The 30-meter telescope, first light is complicated to foresee because there's a lot of hesitation and difficulties with picking the site for the installation of this specific telescope. The takeaway here are that telescopes are obviously all big, and we get significant advantage from the ELT with its 39-meter aperture, obviously. Although that comes as a cost, it's a pretty complicated optical design with 5 mirrors before getting into any instrumentation. You see that the GMT and TMT went for smaller, simpler optical designs and present some advantages. So, however, the takeaway is that except in the far blue, for which I believe is GMT is going to be significantly better, the ELT is going to collect more photons just simply from the aperture size point of view. by a factor of 0.5 to 1.5 to 3, depending on the cases. However, we get very similar performance in terms of astrometric stability and diffraction limits if the AO actually allows to get to that point. And those three telescopes and their instruments, they can also be represented together in similar plots to the one I showed earlier. And so here you get the instrumentations of GMT in dark blue and TMT in a lighter shade of blue. The three in addition, so we do cover similar wavelength and coverage, and also attempt to go for very high contrast mode. That seems to be one of the dominating feature of many of these projects. Complementarity is that the GMT is optimized for a larger field of view of probably around close to 20 arc minutes and gives access to the UV. The TMT is really going to push for AO performance from the get-go, and is going to try also shoot for a shorter wavelength as well as focusing on the near infrared. The ELT is really the sensitivity and angular resolution machine that is going to
continue with a complementarity with JWST. So here too, there are very strong synergies between ELT and James Webb. Because in fact, as you can see, so here it's again the same plot where we have added the James Webb instrument. So you can see that ELT and James Webb cover the same spectral domain, which really highlights the complementarity. You can see, however, that they don't sample exactly the same spectral resolution. So maybe as a summary here, the advantages of each facilities. So James Webb is really the key thing of James Webb is really that it's extremely good at long wavelengths, because it doesn't suffer from thermal background as much as the ELT. And as a complement, while ELT works better at short wavelengths, in fact, it covers even shorter, much shorter wavelengths than James Webb, of course. And in terms of spectral resolution, with more collecting power of ELT, you have more capacity for high spectral resolution. In particular, you can see here on this the high resolution spectrographs that will go up to and METIS also, sorry, spectral resolution of 100,000. While for James Webb, the highest spectral resolution is more about 3,000. The other complementarity is in terms of, again, sensitivity and angular resolution. So as I said, James Webb is better in the mid-infrared because it doesn't suffer as much from the thermal background. And as for in imaging, the strong benefit of the ELT, of course, is that you have a much larger telescope, and so you gain a lot in angular resolution for so you can really see much sharper details on your astrophysical scenes with ×6 better angular resolution than James Webb's. And as Franz said, it really helps to push for the sensitivity of the ELT compared to a smaller telescope like comparable VLT observatory at similar wavelengths, or even James Webb for some of the cases for point sources in particular. And again, this is only possible because there are adaptive optic system and a lot of technologies behind this telescope that brings its capacity to the diffraction limits, and that's really made possible by developments that are made in particular in the French community, where we have a very strong team that develop excellent adaptive optic systems that are facilitated by the international community to install this performant adaptive optic system on these complex telescopes. And yeah, as a takeaway, I think here the point that Karine really wanted to stress is that it's really a very exciting project. It's coming up really soon. As you saw, it's really under construction, and it will be on sky in 2028, so literally tomorrow. And it can do a lot of amazing science, and it's really something where everybody can get involved. In particular, we have a lot of assets in the community. As Franz showed, Franz is involved in all the instruments. We have experts and assets in the community that can help, develop your science cases, and it's just an excellent time now to get organized, to think about what this observatory can do for your science in complementary with also existing observatories like James Webb, of course. And I think that's one of the main points that Karen wanted to make. I don't know, Franz, if you want to add anything about that.
Sure, I can just mention the fact that other communities are getting organized. And so there's been already several workshops organized, most notably ELT, which is all about exoplanets and solar system science workshops, where the communities are really getting together and trying to figure out how they can best utilize these instruments. You don't have to think just about the GTO of the instrument. You also have to think about the open time. And now is a very good time to get together. And it sounds like you've already had a pretty good afternoon thinking about those things together. So thanks for the invitation, and we'll take questions if you have any.
We have one.
So thank you very much for this very nice talk. Very completed. And I have one question for you, because you have developed a little bit a comparison, interesting comparison between the ELT and the TMT and the GMT, is that there is one aspect of the parameter space you have not, is about...
Keep your hand higher on the microphone, higher. Don't touch the bottom. Yes, good, that way.
Is right? Okay, thank you. So yeah, so the point that I missed here is the size of the field of view. That is very important for multi-object capabilities, and in particular for Mosaic, this is the main characteristic, allowing you to obtain many sources at the same time. And as you know, this is a very serious limitation of the big telescopes we are building today. So I know the capabilities, of course, of Mosaic on the ELT, and what I do not know, and apparently you have more information, is about the capabilities of the multi-object capabilities precisely and field of view of the GMT and TMT. Could you comment on that, please?
So not about, so the field of view information that we have listed out here is only about the AO enhanced field of view. I would not be able to answer you satisfactorily. Yeah.
So you mentioned that you and other before mentioned that the spatial resolution of ELT will be about 6 times better than that of JWST, and that's just a ratio of diameters. So that means that AO is really perfect. And can we hope that AO will be perfect? I'm ignorant on this.
Well, the AO, the first generation of AO systems, all of the AO systems are using the telescope infrastructure itself to do the adaptive optics. So the M4 mirror, to the deformable mirror is about 2.5-meter diameter. And this is dimensioned to bring the telescope to the diffraction limited state in the near infrared, around 1 micron. So we're not, so yes, you're going to get that level of sensitivity, what a lot of the communities is working on. Yep. Well, well, I guess to really bring it to the level of a space telescope like that of James Webb, you would need extreme adaptive optics, which is something that's only going to come much later with PCS.
Another one? Wait for people. Yeah, that's okay.
Oh, yeah.
Yeah.
for the glow.
And 30 accent.
30 arc seconds for the MCAO.
And 10 arc minutes for. Okay, if there is no more question, you have, okay. No, it's for people online.
Thank you. The
I can't hear you. Well, they're certainly competing for resources, and because US is a big contributor to both, but they are looking for setting the two telescopes in different hemispheres or in complementary places. So that's how they get around this issue. Yes.
Okay, thank you.
Okay, let's one. Thank you.